Hello and welcome to this video on alcohol nomenclature and properties. My name is Kim, and in this video we will rank the boiling points of alcohols. Consider a container of substance A, which is in the liquid phase. The red dashed lines denote a non-covalent interaction that holds those A molecules close together. Applying some energy into the system, however, will break those non-covalent interaction and we get a phase change to a gas. Recall that the boiling point is reflective of the amount of energy added to a system to break intermolecular bonds between molecules so that we get a phase change from liquid to gas. It should follow that the stronger the intermolecular bonds, the greater the amount of energy required to force that phase change. If we consider the types of intermolecular forces that exist with alcohols, we have hydrogen bonds, dipole-dipole interactions or electrostatic interactions between polar groups, and London dispersion forces, otherwise known as induced dipole. We can order these based on their strengths. Hydrogen bonds first, then dipole, then dispersion. Just to be clear, there is one more non-covalent interaction, and that is ionic bonds, which is strongest of the four. We reviewed in another video how alcohols can form hydrogen bonds. Now we're going to see their effect on the physical properties of boiling points. Since hydrogen bonds are quite strong, the more hydroxy groups an alcohol has, the greater its boiling point. If we have a tie and have an equal number of hydroxy groups, we can use other types of intermolecular forces to tell us which alcohol will have the higher boiling point. All molecules have dispersion forces, and in general, the larger the electron cloud due to a larger molecule and surface area, the greater the dispersion force. We're asked in our apply question to place the compounds in order of increasing boiling point. There are no formal charges here, eliminating the possibility of ionic bonds, so we can use the presence of hydroxy groups to look for hydrogen bonds. Looking at our first molecule, it is a 2-carbon alkyl chain attached to a hydrogen, then an oxygen. Remembering our nomenclature rules, when a molecular formula has an oxygen separated from the carbon by a hydrogen, we do not have a hydroxy group, but an aldehyde. Note that aldehydes cannot donate hydrogen bonds, since the hydrogen is not covalently attached to the oxygen. This aldehyde has no hydroxy groups. Our next molecule is propanol, a 3-carbon chain with 1 hydroxy group. Next we have ethanol, which also has 1 hydroxy group. Our last molecule has 2 hydroxy groups, 1 on either end. It might be tempting to think that there is an aldehyde at the left-hand side, but the oxygen is right next to the carbon, making this a hydroxy group. Since the aldehyde at the top has no hydroxy groups, it will be the one with the lowest boiling point. Molecule 4 with 2 hydroxy groups will have the highest boiling point. We have a tie with ethanol and methanol. Recall that dispersion forces will break the tie when there are equal numbers of hydroxy groups. Since propanol is a larger molecule, it will have a higher boiling point, so ethanol will be ranked number 2 and propanol will be number 3. Even better, we can use empirical data to back up our predictions. Aldehyde has a boiling point of 20 degrees Celsius, ethanol at 78 degrees Celsius, propanol at 97 degrees Celsius, and ethylene glycol or diol has a boiling point of a whopping 197 degrees Celsius. Great job working through this question. Now you have all the skills necessary to be able to rank the boiling points of alcohols.